Yes. Right. All set. Ready to go. So, excuse me. Today we try to have this one single lecture to cover a few things uh, from the chapter. Well, it's actually chapter 7 to 9. Uh, we will try to go over the fundamental stuff about compressor, about expander, and then we try to also visit the Carnot cycle, try to see in reality what would be the necessary changes we have to make in order to make it more uh, consistent with the applied fluid, which is steam in most of the cases. And then we also want to cover the refrigerator to see the reversible Carnot cycle, what we need to learn in terms of efficiency, in terms of the TS diagram, for example. So that would be today's coverage. But before that, let's try to have a quick review of the previous lecture, which is the first part of chapter 10. So as I have in the uh, review lecture, short summary lecture, we were talking about mainly about the following stuff. The most importantly, the chemical potential. Chemical potential, mu. So chemical potential is the property of the species, uh, whether it's in the mixture, say liquid mixture, I have liquid water, I have liquid argon, and I need to identify the difference between the water and argon, or I have the one single component of water, and I have liquid water, have vapor water. So chemical potential is a property of the species at that specific phase. It's a little bit harder to express that, but when it comes to the equation, then it will be a little bit more obvious. So now we are looking at the mixture. Like I said, a mixture could be the mixture of species or mixture of phases. So if we think about the energy equations that we could use to describe those mixtures, we would typically have the following four. We have internal energy, we have enthalpy, we have Helmholtz energy, we have Gibbs energy. So now instead of describing those energies as a function of two parameters, we need to now include the number of phases or number of species. So typically we try to describe this, for example, if we stick with this Tp and I, then we are going to have the equation, let's pick up the Gibbs energy as the example. Then we understand this chemical potential is defined the partial derivative of dg of the total with respect to the specific component I, while keeping temperature, pressure, and other components fixed. No change of temperature, pressure, and other components. So this is the definition of the chemical potential. But of course, we can utilize the other energy equations to try to define this is du over dmi. Now we need to look at what would be the parameters we have to fix. Right? And then we have this dA, dH over dmi. Again, the problem is we need to understand what would be the other quantities we have to fix. And then lastly, this would be dA over dmi, exactly the same. All right, so this is the first thing we covered. The second thing would be we talk about the partial molar property. Let's pick up the property of M. Then this partial molar property, partial molar with respect to a certain species, and partial with a head. So that partial molar property is defined. There's no way we can manipulate no freedom at all over there. So the property itself with respect to the component I, if this is I, then I, if J, this is J. Then we are going to keep temperature, pressure, other components fixed. So those parameters, those fixed quantities are defined. No way to change. Okay, so you have to satisfy this definition in order to call this as a partial molar property. So the third thing we discussed was we were able to derive a quite useful equation. Now, if I have mu, I, and following the previous discussion, we try to describe this as also as a property. Mu I could be expressed as the property of temperature, pressure, and compositions, right? So over there, we follow the discussion pattern. We try to look at the full derivative and partial derivative of mu I. We realize that this partial derivative of mu I with respect to what? Pressure, while keeping the temperature and other components fixed. That we will receive. This is the partial molar volume of that component. And then we had some discussion moving forward to see how we can utilize this very useful equation for some calculations. We have not finished those discussions, so we'll come back this Thursday to continue those discussions on chemical potential. So before moving on, yes.
On the first bullet point, is NJ constant as well? Like on the go up?
Up.
Yeah, so UI equals DG DNI, and then TP, and N is every other species, right? Except for NI.
That's right. Yes, exactly. Okay. So that notation is a little bit confusing. So this is why I had a note on previous lecture. So try to see this MI. M prime means N1, N2, Ni minus 1, and I plus 1 all the way till the other. So the only component we are able to manipulate would be the one in between. So the Ni is the only quantity we are able to manipulate.
Okay.
The other species will be fixed over there. All right. So the chapter 7 to 9, they are very useful. They are the core part of mechanical engineering when they try to design their processes to figure out energy-related calculations, heat, work, and efficiency. So let's try to see what we have not covered from the previous discussion when we were talking about Carnot cycle, the units, the calculations of the working fluid of Carnot cycle. I hope you can recall a few interesting keys. One is we need to. This is the Carnot cycle. So number one is this is reversible. Right? We need to satisfy this reversible confinement or definition over there. The second is we need to have 4 units of the Carnot cycle. Shown on this slide, we have these 2 isothermal processes. We have 2 adiabatic compressions, and all those 4 units are operating with reversible requirement. Third is the working fluid is not critical to the Carnot cycle definition. So we can pick up any working fluid. And in our previous discussion, we picked up ideal gas. Right? So that is the first 3. We also had a discussion about the calculation of work and heat. So they are very useful to help us to understand what is the efficiency of the Carnot cycle. If you recall, the efficiency is always defined as the desired output, which is the shaft work over here. And the denominator would be the price you have to pay. So here, the price is the input energy from the hot reservoir. So that is the definition of the QH. So you can see that is the payment, that is what you are going to receive in the end, right? So using that heat and work calculation, we are able to simplify those, and we are able to describe this as TH of TH minus TC. So we had some calculations over there utilizing the heat and work calculation. But there's one thing we did not move on and discuss, which is what about now we are not using the ideal gas. We are living in the reality, and we are using some other working fluid. And when the working fluid is moving around, that is the typical problem of a flow process, right? So what if I have a real liquid in the unit? Then this is a typical flow process. Then we understand that from the previous discussions, the flow process would be best described by the energy function of enthalpy. So this is why here we try to start from the enthalpy discussion and try to see how we can have a little bit more understanding of those units involved in the Carnot cycle or any heat engine in the reality. So before that, let's try to have a quick cartoon snapshot to look at the 4 units. So for the Carnot cycle or the real heat engine, we need to combine the 4 units. So here a typical one is we started with this. For example, heat output will be in the condenser. The heat import will be very likely we are utilizing the boiler, right? And we have a turbine to output the work, shaft work we are going to harvest. And then for the compressor, we need to manipulate the fluid when they are changing among their phases. So there we can have the expander or we can have the pump. So those would be the actual units in real life, what we are using. So then what is going on if we have a fluid and we try to understand the enthalpy calculation? So first of all, I hope you still recall this is the general equation. We call this as the first law of thermal for flow processes, right? So here we don't need to calculate the PV work of the fluid, and the work is included in the enthalpy definition. And over here we have this mechanical property, we have the potential change, and then on the right hand side we are going to have heat and work. Again, I want to remind you, we are always using this as the default notation to guide the sign. So this is the system, this would be the heat, this would be the work. So what's the unique feature of the turbine, the one we are going to receive the shaft work? So this is a much simplified diagram of the turbine, where we are going to have the input. And we know that we cannot completely change or convert heat into work. So there we have to have some output of heat over there. But the key is we are going to receive the shaft work. So now if we try to go from this first law of thermal for the flow process, so this is always the starting point. So if we look at that process, when you look at the turbine unit itself, we don't have too much change of the velocity. So here is the inlet and the outlet, the tube will be exactly the same. The diameter would be exactly the same. So there's no much of velocity, the flow rate process. So the kinetic energy change would be 0. And there's typically no potential change at all, unless the problem statement will imply that the inlet of the turbine and the outlet of the turbine, their altitude will be significantly different from each other. Otherwise, the potential energy change, we can neglect that. And then we only have this heat and shaft work. So for the ideal condition, we try to minimize the other type of heat exchange, so that we try to force, this is the so-called adiabatic. So if you try to think about the Carnot cycle, we have two isothermal processes. We have two adiabatic processes. So the turbine is one of the adiabatic process. So this is how we are going to achieve the maximum efficiency as proved by Carnot, right? So here, for this ideal analysis, the adiabatic process will have zero heat exchange, right? So the zero heat exchange is for the turbine together with the input and output with the surrounding. But of course, when you look at the unit 1 and unit 2, they are going to have some temperature difference. They're going to have some enthalpy energy differences. But we are looking at this whole unit. If we look at this whole unit with the surrounding, then there's no heat exchange. Okay, so this is the definition from the adiabatic. So now if we look at the simplified form for the turbine calculation, then this is quite simple, as delta H is the shaft work, and delta H is the enthalpy difference between the outlet and the inlet. Okay, so that is a typical turbine. And I have in the title, sometimes you notice that we have the name of turbine, sometimes we have the name of the expander. They are more or less the same. It's just a small difference between the working fluid. So typically in the mechanical engineering or in the industry, we call this as a turbine when we are using steam, water steam. And if we are using other, excuse me, if we are using other gases at high pressure, then usually we call this as the expander. So their fundamental feature should be exactly the same. It's just to distinguish which working fluid we are using. So this is the fundamental equation of the turbine. It looks very simple, straightforward, as long as we understand the understanding of adiabatic process. So what do we actually achieve from there? Well, now if you include the entropy definition, so entropy is defined, ds is defined, a small amount of reversible heat versus the temperature over there. So we have this reversible for the Carnot cycle, right? Here for the turbine, we are still assuming this is a reversible process. And on top of that, this is the adiabatic process. So the Q reversible is 0, which means the entropy does not have any change when you are moving from the inlet of the turbine to the outlet of the turbine. So when we have the working fluid moving through the turbine, we don't have any entropy change. And of course, keep it in mind, this is the ideal discussion. I'll come back in a minute, look at the real turbine process. So if this is the case, then we can quickly come to the conclusion that the expansion or the process from the turbine is the so-called isentropic process, meaning the entropy would be exactly the same from the inlet to the outlet of the turbine. So we have a new different name on top of isothermal, isentropic, isobaric. Now we have the other name called isentropic, which means the entropy does not change. So what is the use of that equation, the isentropic equation? Well, this will allow us to determine what would be the efficiency of the turbine. So here you can see that we are looking at the ideal reversible turbine, which will satisfy the isentropic definition. And over there, since we are not wasting any heat to the surrounding, so over there the maximum enthalpy change will be converted into the shaft work. So if we are following the ideal reversible turbine process, we are going to have the maximum shaft work. So we are not wasting any heat to the surrounding. This is why the entropy is exactly the same throughout the process. But in the reality, that's not the case. The turbine will have some heat exchange with the surrounding, so that we are going to have smaller shaft work output. Okay, so this is how we come up to the definition of the turbine. So this is the turbine efficiency definition, where we are going to have the ratio. So this is the actual shaft work we receive. This is the theoretical maximum, where you satisfy exactly the reversible and adiabatic process. In the real life, it could be non-reversible. It could be some heat exchange between the system and surrounding, so that you are going to have a smaller shaft work output. So now if you look at this shaft work, and you can easily convert that, this is because of the equation we just derived over there. Okay, so this is how we are going to look at the turbine efficiency by the actual enthalpy exchange from the inlet and the outlet. So you can see that we don't have too many complicated equations over there, but the process will take some time to have a good understanding of it. So let's try to move to this this diagram to somehow guide our reading, and try to look at one example together, which is also the chapter example, which is indeed the reason why I emphasize you should read and finish the assignments before today's lecture, so you could have a second chance to look at the whole procedure of the calculation. So now if you look at the HS diagram we introduced 2 lectures ago. So this is the inlet, where typically we are going to have the superheated steam, and that steam will go through the turbine and will be producing some liquid or other steam with lower temperature or lower pressure in reality. So this is the inlet input, this is output. And if you are looking at this 1 to 2 prime, and you notice that there's no entropy change over there, so entropy is exactly the same between the input and the ideal output, then this is a very typical isentropic process, right? So if you are moving along that process, then you are going to receive this maximum enthalpy change as the shaft work. On the other side, you are going to have real output, so that is the real output. That is the point 2 over there. So that you can see that we are going to shift this slightly to the upwards, where you are going to have a smaller enthalpy exchange between the inlet and outlet. And then the ratio between them would be the efficiency, like we just discussed. Okay, so that is the other way we can quickly check on the HS diagram to see what would be the direction. So one thing you want to take a note and compare with the next unit we are going to discuss is when you have the turbine, usually the inlet will have higher enthalpy. So this is why we can output the shaft work. When you are going to have the other unit we are going to discuss in a minute, then you are going to start with a lower enthalpy, and then you try to apply some mechanical work to increase the enthalpy of that inlet. So the direction will be different between the two units. Nevertheless, let's try to move on to take a look at this example problem to see how we are going to utilize the two simple equations we just revisited or we just derived to see the process of the problem solving. So here comes the problem. It says a steam turbine, this is the turbine, with related capacity of work rate. So that is the work rate, right? So that is the shaft work divided by time. So that is the rate of the shaft work with steam. So this is steam water at inlet condition of P1 and P2. And then we will discharge the outlet into the condenser, which is the next unit of the heat engine, at a pressure of 10 kPa. So that is P2. This is P1, this is T1, P2, but we don't know what the T2 is, at least for now. Assuming a turbine efficiency of this, 0.75, determines the state of the steam at discharge and the mass rate of flow of the steam. And we know this is the definition of the actual enthalpy drop versus the isentropic, the ideal path. And we need to determine the state of the steam. What do we mean by the state of the steam? So when we look at the state, which is the PVT of the steam, right? And when you have a mixture, say if you are having a saturated steam, then you are having both vapor and liquid in that steam. So very likely you need to tell me what is the temperature, what is the pressure. Pressure is actually known. P2 is known, T2. And what is the ratio between the liquid and the water, if this is the steam. So again, this is steam, this is water, and we may have liquid plus vapor of that water. So we need to look at their ratio. And after that, we need to look at the mass rate. So how do we start on this problem? First of all, we need to look at, well, if I know the efficiency, I need to convert that efficiency into the ratio between delta H and delta HS along the isentropic process. So first of all, we need to identify what is the so-called isentropic process, right? And if we know T1, and P1, which is a steam, so that is the superheated steam, then we are able to look at all those values. The internal energy, A, G, H, or S, right? So over there, we quickly realize that, well, this import entropy shall known to us. So if we are going to follow the isentropic process, as we just saw from the state 1 to the isentropic process 2 prime, then we know this is T1, P1. We know this is P2. We don't know the T2, but we know S2 prime is exactly the same as S1. So let's see if this information is helpful. Okay, so this is the first thing you need to quickly realize about the isentropic process. So if we read the solution altogether, we have the known condition of the import P1 and T1. So we can quickly have the H1. H1 will be needed to calculate the delta H or delta HS of the isentropic process. This is the S1. This is the entropy of the inlet, and we know this is the P2. So this is the P2, and we know that we are going to satisfy the isentropic process, meaning S2 prime will be exactly the S1, the value we just read from the steam table. And here comes the concept we are going to use again and again and again in all the problem solving over there. So we know the turbine, the inlet, almost guaranteed that it is superheated. Vapor, pure vapor. But when you are going to bring down the temperature and the pressure of the vapor, you don't know whether this will be pure liquid or liquid vapor mixture. You actually don't know that, and you need to determine whether this is the case. So we always have the assumption that we are going to have a liquid vapor mixture. So this is why now if we look at this 10 kPa liquid vapor mixture, then we don't need to have the temperature to determine the state, simply because now we have one component, we have two phases, right? So when you use C minus pi plus 2, then you would receive 1 minus 2 plus 2, which is 1. That is a degree of freedom, the Gibbs freedom rule, which is if this is a wet steam, meaning wet means mixture, liquid, vapor, mixture, then only one condition shall be enough. Here is the pressure, 10 kPa. So now if you go to this saturated or even the superheated steam table, for the first two columns, they will list the saturated vapor, saturated liquid. So this is how you are going to receive the corresponding entropy values for this liquid and vapor at 10 kPa. Okay, so the assumption we have is, let's try to assume this is a positive value of x2 prime, and if in the reality this is a pure liquid, then x2 prime will be 0 after the calculation. If after the calculation, like we have over here, we are going to solve for x2 prime, and that is a reasonable positive value between 0 and 1, then we understand the assumption is indeed a valid assumption. We are going to receive, after the turbine process, a mixture of liquid and vapor. Okay? So this is the first challenging part of this problem. You have to come up with this assumption and to validate by the calculated value. So here, S2 prime would be moving from 1 to, this is 2 prime. We know this is P2, which is known to us. So we calculated the, indeed we are going to have a mixture. And if you look at the x2 prime, that ratio is, we can quickly understand what is x2 prime. So x2 is expressed. So you can see that if x2 goes 0, then we only have liquid, right? If x2 goes 1, then we are going to cancel the liquid. We are going to only have the vapor. So x2 is indeed the ratio between vapor and liquid. Okay. So that is the definition we always utilize in this textbook. So if this is the case, then we know that we are going to have the x2 prime, the ratio known to us. So the good part is, well, for the 2 prime condition, we are going to have the mixture of liquid and vapor. We utilize their S of liquid, S of the vapor, but we also know the enthalpy of the liquid, the enthalpy of the vapor. Okay? So this is why we are going to use those values. So the 2 value is from the saturated wet, let's call this as wet steam at 10 kPa. And we know their ratio. We can calculate what would be the enthalpy of the mixture over here. Again, this is still 1 over 2 prime. So we know their X value, we should be able to read and figure out of the H2 prime. So that is the calculation we are doing over here. And you can see that we are following this isentropic process. So the enthalpy difference between the two states shall be the isentropic or the maximum enthalpy change we could have for that two conditions. Okay, so we have H2 prime minus H1, which is exactly from the steam table reading, and we know this is the delta HS over there. And now we can utilize this efficiency because we know this is the actual, this is actual, this is the delta H of the maximum. So now we figure out this value. We have the efficiency from the problem. That's not a V that is known or calculated just now. Then we are able to figure out what is the actual enthalpy change over there. Because we need to determine, we know that is the actual is shifted along the same. This is the P2 curve, this is the P1 curve. We know that the actual is shifted along the same pressure curve to somewhere, and we need to figure that out. Okay, but now we at least then we know that for the H2 minus H1, we know what would it be the so that is delta H2, the actual enthalpy change using this turbine. So once we figure that out, then we know this is the exact H2 value over there. Okay. And still we don't know whether this is pure liquid or liquid vapor mixture. So what do? Well, we have the same assumption. Let's try to say this is also wet. Let's see if the X2, now that's not the X2 prime, that is the actual final state. Let's still assume this is of vapor versus liquid, which is X2. So now we know that is still the 10 kPa, right? So the two values of the saturated steam would be exactly the same as the previous calculation. So you can see they are exactly the same. Because we just need to have one parameter, which is the pressure along this path, to look for values for the saturated vapor and saturated liquid over there. The only change is that X2 value. So now we have the real H2. We are going to solve for the real X2 value. Those would be the corresponding liquid, that would be the corresponding vapor, saturation vapor at that 10 kPa. So moving forward, one more step, we are able to solve for X2. And indeed, this is between 0 and 1. Okay? So that is a confirmation that our understanding or our assumption is correct. The final state, the actual final, is also a wet state, having both liquid and vapor. So now eventually we are able to determine the actual composition of that steam. Then we shall be able to read that is still the saturated liquid entropy, that is the corresponding saturated vapor entropy, and we know this is the composition between between vapor and liquid. Then we can calculate the actual entropy of the final output. Okay, so if I try to look at this, this is my 1. This is the isentropic process we have to utilize to take advantage of the efficiency equation, and that is the actual final. Here we have P1, here we have P2, and over there that's a liquid and a vapor mixture, so we only need one parameter, which is P2. Okay, so I hope by going over this example, I have showed you how to start from the problem statement and how to approach one by one of those concepts and calculations. And of course, in order to define the state of the final, we only need to know P2 and X value, right? This is a mixture of this is a two-phase mixture of one component. So we don't need to understand the temperature. If we understand the P2, then and the composition, then the system is completely defined. So the flow rate or the mass flow rate will be easier to calculate now, because now we know what is the actual delta H, right? And the delta H change will be converted into the shaft work. So again, this is H. This is H2. This is H1. Is that correct? Yes. This is delta H of always H final minus H initial. And we are going to convert that part into the shaft work. If you are interested in the shaft work rate, then you need to multiply this by the mass flow rate. Okay, any problem on this one? Someone said something, but I did not catch that. Oh, good. I hope.
Heather has a question.
Yes, please go ahead.
It's in the chat.
No, I did not take that question. Oh, how did you find the shaft? Well, that is provided by the problem statement. That is the shaft work rate, not the total shaft work. Okay. All right, let's move on to the other unit then. Let's take a look at the compressor. So the reason why we want to put the compressor, number one, try to look at the diagram. So you can see that we are having this compressor over here. This is the compressor. Now if you go back to the turbine, that is a turbine, right? So I hope you quickly realize that the compressor is the reverse unit of the turbine calculation. Okay? This is the first thing I want to mention. The second is that we are still starting from the first law for flow process, and we come to the equation of this for the reversible isentropic process, right? And for the compressor, I need to have your attention, which is we are now starting from this normally lower pressure, lower temperature, and we are moving to, with the help of the input shaft work, we are going to increase the entropy of the working fluid from this is the final. This is the ideal case that will require minimal shaft work input. And in the reality, the shaft work input is always larger than the ideal case. So how do we calculate the ratio? Well, we still try to design this as isentropic process. Okay, so you can see that the entropy does not change versus we are going to have the entropy increase if we are going to discharge the heat or exchange the heat with the surrounding. The entropy shall always increase. This is number one. And please pay attention to the pressure. So this is the pressure curve. This is the same pressure curve of P1. So we need to understand that the isentropic process final and the actual process final, they shall share the same pressure. So the change would be very likely would be the composition. Okay. And then on the other side, I do want to review slightly that we have the isothermal process, the isentropic process. So don't feel confused on the two processes. We should have two different curves when we are looking at the isothermal or isentropic process. And then for the compressor, we are using the same understanding to define the efficiency. So the efficiency is, this is the delta HS for the ideal change. So there you can see that we are going to have a smaller value of the ideal gas. No, not ideal process. I try to move. Not necessarily ideal gas anymore. This is ideal process. So this is the ideal process, the enthalpy change, which will correspond to the shaft work input. And in the reality, we always require a little bit more work in order to make the change. So the efficiency is defined as the ratio of the two. So now we are going to switch the order. So now the denominator is the actual. And we correlate the efficiency to solve for similar problems of this compressor process. So this example, the previously discussed example, shall serve as the same example if you are working on any compressor processes. Okay. So again, let's try to take a look at now we are completing the map of the heat engine calculation. So this is for the boiler or condenser. So this will involve only the heat calculation, right? So we have the we try to purposely drive the phase exchange. So over there, this is the chapter 4 calculation. Okay. And over here, this is the enthalpy calculation, and we have to utilize the isentropic process. For both units. Okay. So now with that, we shall be able to solve any steam power plant or heat engine processes. Okay. So there's one other thing I want to go over. That is moving from theoretical thermodynamics to reality. So let's see how thermal is actually very useful to guide our design and improvement in real life. So if we take a look at the Carnot cycle, and if we try to put it into the other, no longer PV diagram, but this is a TS diagram. Okay. So if we look at the TS diagram, if we identify the two isothermal processes and two adiabatic reversible processes where you are going to have the same entropy, right? So now we understand that the two adiabatic processes will be corresponding to the isentropic processes that will happen in the turbine, compressor, or pump, or expander. So now if we try to look at those, we have this TH, we have this TC. So over here, this curve itself, this curve is the liquid vapor coexistence curve. Over there, we are going to have liquid. Out of the curve, we are going to have vapor. In between, we are going to have liquid and vapor. Okay, so let's try to see what is going on. First of all, I'm not going to read those notes. I think we have discussed that when we talk about the Carnot cycle, what is going on for each unit. But I think the most interesting part is over here. One is this path. The other is this path. Still involving the turbine and pump, the discussions. So we realized two technical challenges in reality. One is if we are going to use a turbine and a pump, so here is the turbine process, here is the pump. So if we look at the turbine, those blades are usually made of metal components. Then if we are going to deal with this as so that component 3 over here, we are going to have a significant amount of vapor and liquid, especially for the liquid. Then we realize that the erosion would be quite bad. So the turbine, after a few years, we have to replace the blades. That is not too encouraging for the real application. So this is challenge 1 over here, simply because the liquid water at relatively high temperature over there would be quite reactive with all those metal materials, metal and metal oxides, even with the steel itself. The second challenge is over there. So we need to have the pump to compress the working fluid from the state 4 to the state 1. And you realize that here we are also dealing with the liquid vapor mixture, right? Liquid vapor, liquid vapor over here. So we have the funny challenge over there. So if you are using the pump and you have to compress the liquid and vapor is occupying a much larger space. So that means in order to achieve the good mass transport, you are going to have a huge tube in order to transport all those vapor phase. And you don't like carry a much larger volume to use for the pump, right? So here the challenge is we try to receive a much better performance of the pump, and in reality we want to reduce the space occupied by the pump and related tubes. So here we try to minimize the vapor composition, while over here we try to minimize the liquid composition over here. And we don't know those two challenges until we put the theory into real device, into real application. Then we realize that, no, that's not really good in terms of the economics. So we have to make some changes. And that change is proposed by Rankine. And I hope now if you think a little bit harder, we are actually able to reproduce the sort of Rankine. So for example, from the process of 2 to 3, we need to get rid of that liquid component as much as possible. So what do? Well, we just extend. I make a curve, that is because after the phase transformation, we are still following the same pressure, but we are not going to extend that straight line or horizontal line, but this is curved a little bit over here. However, they are still on the same pressure diagram. Okay, so if we somehow extend the final a little bit over here, then if we try to move the pass down, then of course over there we are going to have a pure vapor. So you don't need to worry about the erosion or the corrosion or the reactions in the turbine process, right? But also we want to save the energy, so we don't use too much energy to produce a super heated vapor, because along that path it will cost energy to keep increasing the entropy of the superheated vapor. So we want to make sure that we are at the right condition, so that when we move to the state 3, then we are quite close to the saturation point where we can easily ignore the component of liquid, right? So we claim that on this curve itself, we have the liquid vapor saturation, but slightly move this to the right, we are going to get rid of the last liquid drop. So if we are able to stay over there, that should be my best option. Okay, how about the next one? Well, the next one is also very similar to that sort. So if we are going to move this state 4 slightly to here, okay, instead of an obvious liquid vapor mixture, but if we try to push this to the liquid vapor saturation curve, then over here I can also easily claim that we almost have no vapor existence over there. Then we try to move up to this, and of course for the same reason, we don't want to push too hard that we are moving over there. Again, we are going to cost some energy in this condenser process. We are going to provide more shaft work in order to push this to the pure or the super cooled liquid phase. So this is why this should be my best option, my best choice. Okay, so that two changes are exactly from the Rankine cycle. Okay, is that making sense? No answer as usual. So move on. If this is the understanding, then I'm going to leave this Rankine cycle. Try to read the description I have on the 2 slides, including this one. Okay, so you are going to shift. So this is the original design, the Carnot's design, which is theoretically perfect, but in reality, we have to try. We have to put a little bit more of the energy along the along this process to move this a little bit further, and along that process to provide a little bit of shaft work. So we are going to increase the lifetime of the actual units. Okay. And then again over here, you are still looking at this is the perpendicular. This is a truly vertical curve. This is the actual curve. So there you still need to design the isentropic versus the actual process to understand the efficiency of the turbine and the efficiency of the pump. And here, this is a little bit shifted, but this should be this perfectly vertical versus this is the so-called actual path with respect to this isentropic process. So this is the that design is the actual engine. So nowadays, for any heat engine, any engine involving the heat and work exchange, we are following that that design. And this is really the power of theory from thermodynamics. And if we combine the other considerations on material property, then we come up with this very beautiful modification, and we are very happy over the past 100 years or even longer for this Rankine cycle design. So the last part, I want to quickly go over some refrigerator process. So I have those notes, and I trust you've read or you will be reading, so I'm not going to go over this. So if you think about the key difference between Carnot heat engine and Carnot refrigerator, so you can see that the obvious difference is now we try to absorb heat not from the high temperature object, but from the low temperature object. And then we are not going to produce shaft work, but instead we are going to import, we are going to provide the mechanical shaft work to drive the process. And in the end, we are going to discharge the heat, excuse me, at this high temperature part. So this is indeed the reversible Carnot cycle. Or we have the Carnot cycle being by default a Carnot heat cycle. Okay, so that is the only change we are doing over here. And all the 4 units, they shall be exactly the same. We still have the 2 isentropic, no, isothermal processes, right? Temperature will be temperature, dt would be 0, dt would be 0. We still have the 2 adiabatic process where ds would be 0, ds would be 0, right? Or we call this as isentropic. So now we have the adiabatic or isentropic, and we couple the 2 units with the 2 isothermal processes. Okay, and you are still able to do the same calculation of heat, work, including the composition. So that too we just added by today's lecture. Okay. One last note about this curve. If you compare this with the standard Carnot heat engine, then you can see that the flow direction is changing from the curve shown over here. Okay. So I put that together on this this diagram over here. So this is the heat engine, this is the direction, this is the import, this is output, and we are going to produce shaft work. So this is the shaft work. And on the other side, when you look at the refrigerator, this is the heat input, this is the heat output, and we have to provide shaft work to make it happen. Okay, so we are paying our electricity bill to use the refrigerator in our home. Nothing special, but I hope you are not too surprising if we are looking at, instead of the TS diagram, if you look at this PV diagram, then we should be able to figure that out. So that is still the see the slides of Carnot cycle discussions. So those would be the diagram we were using when we try to look at the Carnot cycle in the second law and the third law discussion. So over here, let's try to understand the efficiency of the refrigerator. We usually call this as coefficient of performance, this omega value. We have multiple omega values. I think omega is a good letter, so we have been utilizing this again and again. Where was the first case of the omega? We try to look at the 3 parameter, right? 3 parameter CST, corresponding state theory and corresponding state or corresponding state principle. Then we use this as the eccentric factor, right? So here, if we try to define the coefficients or the efficiency, we're always interested in the input and the desired output. So the actual input we have to put in is the shaft work, and the desired output is how much heat we are going to absorb from the lower temperature. So that is the purpose of using the refrigerator to lower the temperature of the object. So we try to compare the ratio to see what is the best performance. So this is number one. If you think about all the efficiency values we have been talking about, I think we are along the same line. We try to evaluate what is the pay in order to make a change, and what is the actual output we are going to receive. The ratio is always the efficiency, and of course, the efficiency is higher, the better, right? So this is number one. Number two is if we try to follow the discussion of Carnot cycle, we understand that the heat and work can be replaced by simply their temperatures. So I hope this is not surprising that this should be QC, and this should be the QH minus QC. This should be TC over TH minus TC. Okay, this is the efficiency of the Carnot refrigerator. How about the Carnot, the Carnot heat engine? Carnot heat engine is what? Is TH over TH minus TC. Okay, sort of similar, but slightly different. Although the idea behind those efficiency definition would be exactly the same. Okay, so I have a simple example on the coefficiency of performance regarding the Carnot cycle, and I think it's nothing special. If you realize what would be the equation, then just plug in those values and you will have it. We have a few minutes. I want to bring to your attention that by finishing this lecture, we shall be able to revisit all the previous problems I've had in the thermal exams regarding the whole loop of those 4 units, and trying to correlate and understand their energy, work, and efficiency calculation. So I also want to bring to your attention that in the previous years,